In this video, I want to take a look at how we distinguish between different types of critical points. Are they maximums? Are they minimums? Are they saddle points? So if you remember back in Calc 1, we found critical points. And again, you didn't know just because the derivative was 0, do you have a local max or a local min, right? But we used the second derivative to look at the concavity. If it was concave down, so the second derivative was negative, then you must have been at a maximum. If it was concave up, that is second derivative positive, then you must have been at a minimum. So we're going to do a similar thing here, but there's more than one second derivative now because you've got, the second partial derivatives with, xx or xy or yx or yy, and, how's that all going to be put together? Well, here's what we're going to do. It says if f of x, y is a function of two variables, for which the first and second order partial derivatives are continuous on some open disk containing the point x0, y0, and suppose that both the first partial derivatives are equal to 0. So you're at a critical point. Not just a critical point, but the special type of critical point where the derivatives are equal to 0, right? There's another type where one of the derivatives might not be defined. And so we define the quantity d, where d is the second partial with respect to x, evaluated x0 and y0, times the second partial with respect to y, evaluated at x0, y0, and then minus the mixed second partial, evaluated at x0 and y0, squared. Now, the theorem says that if d is greater than 0, then this is a local max or a min. And we decide by looking at the second partial with respect to x. If that's positive, that means this is concave up in the x direction, so it must be a local minimum. Likewise, if xx is negative, that means it's concave down, and we must be at a local maximum. If this d turns out to be negative, then this is a saddle point, and if d equals 0, then this doesn't tell us anything. Right? And that's reminiscent of the second derivative test that we had in Calc 1, because if the second derivative was, as we said, positive, that was concave up, so you're at a minimum. Second derivative was negative, that was concave down, you're at a maximum. And if the second derivative was 0, then it didn't tell you anything. It might be at a max, it might be at a min, it might be at negative. Okay. Now, I want to point out that this choice of looking at fxx is arbitrary. Right? The thing is, if you're at the stage where d is bigger than 0, look at what d is. It's the product of fxx and fyy minus a positive number, right? Because no matter whether fxy is positive or negative, when you square it, that's positive. Right? So minus that is a negative number. And so if you've gotten to the point where d is positive, that means this has got to be positive. The fxx, fyy product has to be positive, which means both of them either have to be positive or both of them have to be negative. So if you're in a situation where d is positive, then the fxx and the fyy are agreeing with each other that this is either concave up, or both of them are positive, or it's concave down with both of them negative. Okay? So the choice of fxx here is arbitrary. You could check fyy as well. And the thing is, those two by themselves don't determine whether this is a max or a min, because you could have it so that it's concave up both in the x direction and in the y direction, but that in between it's going down, so you'd be more like a saddle point. So it takes all of this, that the fxy is sort of telling you what's going on in between the x direction and the y direction, right? So let's see how this works. I'm going to use the same function that I used in the previous video, so that we've already done a fair amount of the work, right? This was the function fxy minus x cubed plus 27x minus y cubed plus 12y. We found in the previous video that, well, whether we did it or not, the partial derivatives of here, what we found was that the critical points, that is where you could get these partial derivatives equal to 0, were at 4 different points. 3, 2, 3, negative 2, negative 3, 2, and negative 3, negative 2. Now, by looking at the graph and at the contour plot, we could tell that one of them was a local max and one of them was a local min, and two of them were saddle points. But let's see how this D thing helps us out. So fxx here, so take the partial of this with respect to x, you get a negative 6x. The fxy, take the derivative of this with respect to y, well, of course that's 0. Likewise, the partial of y, this fyx would be also 0. And fyy is the derivative of this with respect to y, and that would be negative 6y. So D is the product of fxx, fyy, minus this one squared. So that is 36xy. So this D is going to be different for different places, different xy you plug in. So looking at my 4 critical points, 3, 2, when I plug it in for x and y, 36 times 3 times 2, I don't even care exactly what it is, I just care that it's positive, right? Positive times positive is positive. So this is either a max or a min. So I look at fxx. Well, fxx is negative 6 times 3, which is negative. That means negative 18, but I don't care. It's just less than 0, which means this is concave down in the x direction. So this must be a local maximum. Okay. Notice I could have done fyy, because this would have been negative 6 times 2, which is also negative. So that's still telling me concave down, local max. For the point 3, negative 2, D is 36 times 3 times negative 2, which again, I don't really care exactly what it is. What I care about is that's less than 0. It's a negative number. So being negative is telling me this is a saddle point. And indeed, that's what we saw in the previous video. Negative 3, 2, plug that in. Negative 3, 2, again, that's negative, saddle point. And the negative 3, negative 2, with both of these negative, that's positive times negative times negative. The result is positive. So this is either a max or a min. Looking at the second partial in the x direction, it's negative 6 times negative 3, which is positive, which tells me concave up, which means I must be, if I'm horizontal tangent in a concave up situation, means I must be at the bottom of a valley, so I'm at a local minimum. Right? One thing I want to notice here is that the formula for D is probably, I find it easier to remember in determinant form. That is, if you think about this determinant of a matrix where the entries are fxx, fxy, fyx, fyy, right? Those partials, the second partials. These two here will be the same. So when you do this one times this one minus that one times that one, those two are the same, and you can just write it as one of them squared. Right? So that's the way I remember this formula, is to write it here. We start with the partial of f with respect to x, taking both the x and y partials of that, and then you have the partial with respect to y and the x and y partials of that. Anyway, take that derivative. So there's one example of how you can use the second partial derivatives to determine whether your critical points are maxes, mins, or saddle points. Calculate that D, and then look, is D positive or negative? If it's positive, it's a max or min. If it's negative, it's a saddle point.